Good afternoon, all. Let's resume where we have stopped last time. Yesterday, we have talked about the queues. I'm sure you found that topic easy, and as you have already done the stack implementation, so I'm sure all of you could easily do the queue implementation. Of course, some of you could have probably found some difficulty in implementing the compact operation. So I'll show the compact operation code also and demonstration of the sample code. So that we will see once we discuss some important concepts. So yesterday I have stopped talking after starting a concept related to circular queue. And I told that, yes, what is more important is that can you think of a situation where circular queue fullness versus empty condition will be there. So we are going to now discuss further upon that. Just to have a connectivity, let's recall full or a circular queue means that whenever you reach to the last boundary, you try to go to the initial boundaries as long as the space allowed. So your front as well as rear, they will keep on rotating in between boundaries of 0 to max minus 1. As soon as it reaches to max minus 1, so it will be revolving back to the previous 0th index. And to implement that, if we said that instead of simply writing rear plus plus etc., we will be not writing it simply in this form, but we will write it as rear is equal to rear plus 1 percentage max. So that will ensure that the value always remains in the range of 0 to max minus 1. Hence, ideally, based on that, we can also smell that I want all these values to be in between 0 to max minus 1. So probably my initial values of real as well as rear as well as front should be taken as some range in between 0 to max minus 1. Anyone can be used. So maybe we can think of doing rear equal to 0 and front equal to 0 initially instead of taking it as minus 1. Of course, minus 1, you could think that probably can work, but if you take minus 1, that in special situation can create a problem. So that we will talk later. But yes, let's go to now circular queue where we have this implementation done and we want to understand where the fullness can be checked. In normal queue, my full was if rear equal to max minus 1. Obviously, now that no longer is valid. So it cannot be full condition. How the full condition will be? Obviously, it is connected to front versus rear positions. For emptiness, I can easily see that earlier empty I said was if rear equal to front. And probably I can smell or I can guess that this should be okay. Why it should be okay? We can verify. Let's say initially I initialized it with 0. Initially it is empty, condition is okay. And initially empty, both are 0. So still condition okay. And this condition will still work. Let's take a situation where we insert some data. So let's say rear was here at 0th location and front is also here. Say first time you insert something. Your normal insertion will mean obviously rear to be incremented. So let's say you store 5 value here and rear changes to this. Then maybe let's assume you again insert something and then obviously rear changes. So my rear is now at index 2 and front is at index 0. Now you can notice for the first time insertion will happen from index 1 onwards because rear is initially 0, but we always increment rear before insertion. So it doesn't matter. Of course, after circulation, this location will also get utilized. So no matter from wherever we start, it is okay. Now I say front. So let's say you tried, so you have done insertion 5, done, insertion 7, done. Now you say delete. Delete will mean front to be shifted. So front will come here and 5 deleted. 5 gone. So this value is gone. Now you say again delete. Delete will mean again front to be shifted, and front also comes here now. 7 effectively deleted, and again Q is empty. Now if you see, when Q is empty, again rear is equal to front. Rear is also at this index 2, front is also at this index 2, and I can see that both are again equal. So for emptiness, I can easily say that for emptiness, I don't get any problem, and I can easily check if a front equal to rear. That becomes an empty condition without much of a problem. But what about full? Of course, I need a replacement of rear versus mx minus 1. So here there is a catch now. Assume that you have a Q like this. Let's say at some point of time, Q was empty. So that empty meant your front was here. And I say your rear is also at present here. Q is empty. Now what happens? Let's start making it full. Assume you put the data here, say, then you keep on inserting the data. So how do you insert? Your front remains here. Let's say this is some index 5. Could be any index because it can be empty at any point and at any index. So front is 5. Let's say you store data 11. Your rear reaches here. Then you store another data, let's say 15. Rear will again shift. You again some store data 30. You store data 20. Rear is shifting automatically. So next time you reach rear here, let's say you store data here also 40. You store data 30. You store data 50. Now, rear is at this point. So effectively, only index 5 is empty and rest whole is full. So my rear is effectively currently 4, front is currently 5, and I can see all locations except 5 are full. Now, at this point, just imagine if you insert. Of course, I have an empty location. So let's say you try to insert 10. If you try to insert 10, what will happen? Your rear will be incremented. You have here 40, you have 30. So I have say some data because I'm saying this is index 4. 4 means 0, 1, 2, 3. So let's assume we had some data here, 25, 35. This is index 0 onwards. So all those have been full, and now my rear is at index 4. So that means this is 0, 1, 2, this 25 is also okay, 0, 1, 2, 3, and this is 4. So rear is 4. That means I have here 25, 35, 40, 30, 50. And this is your rear at present. Now rear will be incremented to insert 10. That will mean rear reaches to next location 5. This is index 5. You will store 10 here and 10 gets stored. Remaining is already full. And your front is also at this point. So now see, front equal to 5. Rear is also 5. So Q has become full. And at present, front is equal to rear. So earlier, I planned this to be a condition for empty. Now I can see for full also the same situation happening. So I will not be able to differentiate between full versus empty. The condition for full and empty is coming out to be same. and that we can't afford. Hence, we have to think of a solution. So what is the solution done? So the solution done is the queue is always filled with one location always left. Left means unutilized. I will not fill the queue to the full capacity. I will say in the earlier situation, if my front is at 5, I say I will allow rear to go up to index 4, and my rear can be here till now, okay, but this location will never be allowed to be full. And I say if next location to rear is front, it means it is almost full. Except one location, everything is full. So I will say next to rear being front means I will conclude it to be called as full. So I will differentiate between my saying full. Full means if I have max as 100, I will say maximum 99 locations will be full and one location will be left empty. What does that mean? That means that every time I will check, what will I check? That whether I have reached to accept one location, everything full or not. So if I say I am implementing my insert into circular queue with, of course, int val, etc. First, I have to check full. How to check full? So I say next to rear. Which is the next to rear? Rear plus 1. But not rear plus 1 alone is never sufficient because you might go out of max limit. So whenever rear plus 1 is to be used, actually it is always to be used with the max percentage. So I say if rear plus 1% max equal to front, this actually means full. Else I am allowed to do insertion. Insertion will mean now effectively rear to be incremented, and rear to be incremented always now will mean not rear plus plus, but rear plus 1% max. And then, of course, now my queue, wherever I have implemented the array, and in that at rear position, I will store the value. And this way, I will be able to utilize all locations without compaction needed. Disadvantage of compaction was that it needed a loop, and in this case, without a loop, it's all unit time operation, and I am able to do utilization of all memory which got free through deletion also. And ideally, we want operation to be unit time always. Similarly, I can have my delete from the circular queue also to be implemented similarly, and the emptiness I condition I know, and front to be incremented will always mean front to be made equal to front plus 1% max. Rest remaining similar what we know. So we can easily implement this. So with this, I will leave here and give you one homework, that implement the circular queue and its operations. Using repeated choice, you can again give. So in main, you can give repeated choices to display and insert and delete and verify that it works. So I'm sure you can easily implement this. Then going further, now we say, till now we talked of a single stack, single queue. In many applications, we will require multiple stacks and queues. So we will be willing to implement multiple stacks and multiple queues. Of course, that can be done by taking multiple arrays, multiple top variable or multiple rear, etc. So that can be one way. Every stack and queue being independent and multiple variables created and done one way. So in the all stacks, all multiple ones are independent. Let's say if I'm talking of stacks, so all are independent, separate variables. Yes, that will of course work without much of a problem, nothing more to be discussed. But sometimes we might have space constraints. Space constraint means memory constraints, and we want to do optimal solution. So sometimes we want an efficient solution, and efficient solution primarily always means the time to be efficient, space to be efficient. Time, of course, I know that we are already saying unit time operations, so that is the best operation, and we should try to keep the operations to be always unit time, so we can afford or we will always prefer that. So my efficiency always means time and space to be minimum. Space doesn't mean the space I'm talking of as the lines of code. Space I'm meaning during runtime, how much variables take the space. During runtime, how much space or memory needed by variables. So if I have taken variables like big arrays, 2D arrays, 3D arrays, they take more time and they mean more space or more space complexity. Like in case of a merge sort, we said we need extra arrays, so that adds to space complexity or less efficiency in terms of space. So sometimes it will be needed that you want multiple stacks to be in a single array. And similarly, multiple queues also. So we will understand one by one. So constraint is, I'm already told that you have only one array. That means, say I am declaring int ARR as max. Now, you have to give, let's say, n stacks in this. So ARR should be able to be utilized for n stacks. N could be 2, 3, 4. Let's say I mean n to be 4. If I say 4, let's assume I have this array. So this is my ARR, 0 to, let's say, 99. So total 100 elements are there. And I want 4 stacks to be implemented here. If I say 4 stacks, so ideally I will say maybe approximately or precisely 100 by 4 means 25. So 0 to 24 can be your stack 1. So my stack 1 will grow in this direction, 0 to 24. Then I can have similarly 25 to 49 as stack 2. 50 to 74 as stack 3. And 75 to 99 as stack 4. So effectively, I precisely have divided the total space into equal area for each of the stack, and through that, I'm able to do that. What will that mean? Once I know this, I will say I will need 4 variables, top 1, I will need top 2, I will need top 3, and so similarly top 4. I should know what should be their initial value. Then I will need push 1, which will be used to push the data into stack 1. 2 stack 1 effectively means into the same variable ARR, but at different locations. Top 2 also to be given some value, but push 2 will be storing into stack 2 at a different address. So all that we have to make that. So let's see how it will happen. Ideally, when I draw this figure, I have explained everything to implement this. Ideally, this explains everything. When I said that you had, if size was 99, 0 to 99, and if I say this, I have already said up to 24, it is a stack 1. So in your ARR array, stack 1 means 0 index to 24 index. So that tells your empty condition also, that tells your full condition also, that tells everything. Stack 2, 25 to 49. That again tells your empty condition, your full condition, etc., etc., and so and so. So ideally, everything is defined. For example, in this case, my what should be top 2 equal to 25 or 24 to be precise, because from 25th onward, this will be saved. And anytime my push 2 has to work, if not full, effectively nothing special to be done, I will say ARR plus top 2 equal to val. Not full. When will be it full? Full means effectively I will say if top 2 is less than equal to 49, or to be less than 49, because 49th will be the last location where I can fill. So I will say if top is less than 49, it is not full. So effectively, whole coding is well defined through this process. Intentionally, I'm not writing the full code. I want you to try, but I say, how do you know these boundaries, 25, 50, or 49? So I will say that I can easily find. I can find size for each of the stack. Each of the stack will be of size max by n. Like I said, 100 by 4. So size becomes 25 in this case. If max is 200, it will become 50. If n is a 10, size is max is 100, then 10 stacks. So 10 size will become for each of them. My first stack boundaries are well defined now. 0 to size minus 1. Stack 2 effectively starts with size and goes up to 2 into size minus 1. Similarly, stack 3 will start with 2 into size and will go up to 3 into size minus 1. For example, stack 2, I said, it could start from 25 and could go into 2 into 25 minus 1, that is 49. So this is how my boundaries are defined. So effectively, stack 2 starts where stack 1 ends. And same statement is true for all others also. So this concept can be utilized to implement multiple stacks. But remember, every push 1, push 2, push 3, push 4, every pop 1, pop 2, pop 3, pop 4, they will use the array ways will be same. The indexes will be different. Indexes could be top 1 based or top 2 based or top 3 based or top 4 based. But array is the same because that's a condition. So I'm sure you can easily implement this. Similarly, there can be multiple queues in a single array. In one array. So that will mean if I have got this much big array for storing multiple queues, let's say I want n queues, so I can always have the same space optimally utilized among all of them. For example, if it is 0 to 99, my n is 5, so I will say 0 to 19 will be Q1 up to 19. So 20 locations used for this. Next 20 used for Q2. That will end at point 39, start with 20. Similarly, Q3. Similarly, Q4 and Q5. So this is boundaries again I can define. For example, for Q2, my front and rear are to be initialized. If they are not a circular queue, if they are normal queues, earlier I used to have front to be -1. Now effectively it will be 20 minus 1. This is my boundary 20. From here Q actually starts. So my front 2 variable will be 20 minus 1. Similarly, rear 2 will be 20 minus 1. And fullness condition will mean rear 2 to be going up to 39, 40 minus 1. So if my rear 2 is less than 40 minus 1, it means there is a space left, because up to 39 it can go. Rear 2 less than 39 means next location to rear can be used. So that will mean not full. And not full will mean I can increment rear 2 plus plus, and then I can store into ARR itself equal to the corresponding value. So if I want n queues to be implemented, ARR is common, and I will have front 1, queue or rear 1, insert 1, insert Q1, similarly delete Q1 as one set. Similarly, front 2, rear 2, insert Q2 as a function, and delete Q2 as another function. And similarly, others also. So for each queue, this will be separately available. And I can definitely make the implementations like this. Going further, I'm giving you another option for the implementation. That one way could be that you implement separate insert and delete functions for each queue. But I can say equivalently, it is possible to write one insert queue function, and you tell here the number I along with the val, where I tells queue number to which insertion to be done. For example, if I say I write insert Q 2 and 25, it means that insert 25 into Q2. So that internally should be able to use front or should use rear 2. And similarly, if I say delete Q from 3, some value, that will mean it should be able to delete from Q3. That will also mean it should internally use front 3. So I want you to think in a way that you write one function void insert Q, insert into multiple Qs. Let's say I'll say insert multiple Qs, int I and int var. And now you write here code so that insertion happens into proper queue. That will also mean fullness also to be checked. If not full, only then insertion to be done. I say all that can be mathematically possible to be defined, and each boundaries can be identified through this process without much of a difficulty. And you can have rear also as an array of n rear variables. Similarly, you can have a front also as an array of n different variables. So if n is a 5, you could say I need 5. So effectively, your rear I and front I can be the corresponding indexes to work over logical queue I, where all queues are in the same array physical. So physically, this is my Q1. Next is Q2. And so and so. To be precise, if you need that, then you will say one extra rear variables because indexes start with 0. So ideally, I should have here n plus 1 because rear, I am saying here 1 to n. So that will mean this size should be 6. This also should be 6 because in this case, 1 to n is being used. So my total array declaration has to be from 1 more than what is n, and that will only give you the indexes from 0 to n, out of which you will use indexes 1 to n. I think that much is good enough to tell you, and try yourself to implement this way. What I am going to discuss with you is something more than this, which says that let's talk of a special situation where I am willing to have 2 stacks in one array. So, of course, method 1, we have just discussed that I will say I have total memory. So, my stack 1 grows like this and goes up to middle. Say, let's say 0 to max by 2, 49. Approximately max by 2 minus 1. And second stack obviously goes from 50 to 99. Of course, in terms of max, it can be done. So I say stack 2 will be like this. That will mean initially, I can easily say that top 1 will be declared as -1 and top 2 will be equivalently declared as 50 minus 1. And accordingly, my push 1 and push 2 can be declared. Accordingly, they can be implemented. And similarly, pop 1 and pop 2 also. Or equivalently, you could have one push function where you tell the number and the value, where you will tell I equal to 1 means push into stack 1, and I equal to 2 means push into stack 2. That way also you can do the coding. I say you to try both. But I am going beyond that, even a smarter method than that. Can I do even better than what we are doing now? And the answer is definitely yes. Above method has a restriction that both stacks can have maximum 50 elements. It is possible that stack 1 has some free space, but stack 2 got full, or vice versa. I say even I will be able to relax in this situation. I'm sure some of you are able to guess well. Yes, you can smartly play that there is no in-between boundary. No stack ends at middle. It goes in the reverse way. Stack 1 grows like this, the way it was. But I don't say stack 2 to grow from here. I say let stack 2 grow like this. Stack 2 grows in opposite direction. So the advantage will be that it is possible that if a stack 2 has only 20 elements, it can happen at some point that your stack 2 was going up to this only, top 2 has reached here. This means this much location is full. So your top 1 can grow up to this boundary. Let's say if it is 80 to 99, so top 1 can go up to this, and vice versa also. Let's say at some point of time, your top 1 has gone up to this, meaning that this stack 1 is full up to this point only, let's say 16. Then your top 2 has a flexibility to grow up to 17. Up to 17, it can grow in the reverse manner. So you have that freedom to adjust the boundaries. Now, in this case, obviously, I will say my ARR array being common. So top 1 will be initialized as -1, but top 2 will be initialized as max outside of this array. This is 99. So top 1 is on the left side outside of the array, and top 2 is on the right side outside of this array. And my push 1 will actually use top to be incremented, or plus top 1, whatever you say. Say, for example, we will be probably using plus top 1. But for push 2, we will be doing minus top 2. First time top 2 is max 100, so it will become 99 first time, and push will happen. Next time it will become 92 and push 2 will happen, and so and so. So both can work simultaneously. And empty condition, obviously I can easily define. Full condition, I have to think. It's no more the fixed boundary. I will say fullness will happen when? Say at some point, if your top 1 is here, it means this location is already full. This is filled. This is not empty, filled. So if while coming from other side, if a top 2 also reaches here, then I can mean it is full. So a condition something probably if a top 1 equal to top 2 or maybe top 2 minus 1, probably that can mean the fullness. I can verify by thinking more logically, but this could be some hint which I want you to try. So once you know this, after this, now it is possible that you can easily try to implement this. So I'm giving you second homework. So my homework 1 was circular cube implementation, and homework 2. I say implement 2 stacks in 1 array. There are 3 alternates. Of course, there are 3 alternates. What are 3 alternates? Based on method 1, I have alternate 1, which means you will implement push 1 separate function, push 2 separate function, and so and so. And method 1 means fixed size for each stack. Just we have discussed that. Method 2 can also be implemented using another alternate that you write one push function where you pass your I also to find which stack number to be used for push. And third alternate is corresponding to method 2 where the size is variable or dynamic based on the other stack also. So both stacks will become full. Otherwise, each of them will be able to push in case some space is left. This alternate I say as alternate 3. And here you should be able to implement push 1 and accordingly push 2. Of course, this also there can also be alternate 4 where both of them can be coded using a single module also. So that's also one and the same thing. You can try that. But I say at least one of the one alternate should be used, and good students must try all 3 alternates. So I will say implement using all 3 alternates. So having said that, I think I will wind up here and stop my discussion and try all these. In the next class, we will discuss some of the codes related to the demonstration and talk of something more. Soon we will be starting with the pointers. So get ready. Those who have not practiced or revised the pointers, they should go and start revising pointers. Soon we will be starting with pointers and very important discussion data structure about linked lists. Bye-bye. All the best to all of you. Try and implement all these.